Hey everybody, this is Alex Merced, developer advocate at Dremio. What I want to do is just kind of do like a sort of a whiteboard kind of explanation of how Apache Iceberg works and sort of like what is it. Okay, again, I'm one of the four authors of Apache Iceberg, the definitive guide. So if you want to get a free early copy of this O'Reilly book slated for early next year, right there's the QR code. You can scan that and get a early copy of the book. I think there's 4 chapters up. There's probably a couple more that should be added to the early release soon. So always check in regularly because we're constantly adding more chapters to that early release book, which contains very in-depth explanations on sort of the context and what is and the whys and the hows when it comes to Apache Iceberg. Okay, now with that, first let's just kind of talk about like sort of like what is Iceberg. So at the end of the day, Iceberg is essentially, okay, let's imagine you have lots of files. Okay, so here we go, we have files. Okay, and you have lots of them that make up like a single data set. So you may have like this, maybe the data set on, every voter in the United States. Okay, this may be a really large data set. So it's split up among many Parquet files, many ORC files, many Avro files, whatever file type you're using. And generally, you're going to want to run analytics on this. Now, you could ETL all this data into a data warehouse, which kind of has its own internal machinations for sort of cataloging the data set, for generating metadata to optimally query that data set, etc. One of the issues, then you're making a copy of the data, okay, because you're making a duplicate of all these files that are currently, let's say, on your data lake. So essentially, your sort of big storage repository for data, okay. So you're moving it from a copy from your data lake to another copy in a data warehouse. And then generally the data warehouse storage might be a little bit more expensive. The compute to run the query there might be a little bit more expensive. And the thing is that only that tool works with the data there. You may want to use other tools as well because other tools provide other types of benefits, use cases, etc. So this is where we gotta get into the data lakehouse pattern. So the idea is that I would like to query this data using tools that target the data lake or data lakehouse. Okay, so data lakehouse, these could be, query engines that read the data. These could be ETL tools that help us put data in the data lakehouse. Okay, and basically the only thing that makes it a data lakehouse is the fact that now we're doing not just ad hoc analytics on the data in our data lake, we're trying to do sort of the full gambit of data lakehouse or data workloads. Okay, this kind of stuff we would do in a data warehouse. The problem is when it's just a bunch of files, it's really hard for these query engines and ETL tools to kind of figure out, okay, out of these so many files, I really only need to scan these 4 files. Okay, I only really need to scan these 4 files. So it would be much faster if I only scanned those 4 files to run my query. Okay, but if just in a big sea of files, it's not obvious on how to do that. Okay. Now, what used to happen in the past, you would have a format called Hive, okay? And the way Hive worked is you would have what's called a Hive metastore, okay? And so basically any kind of data lakehouse query engine, what they could do is they could hit up the Hive metastore and say, hey, I'm looking for table A. And it would say, okay, this directory, this folder is table A. Okay, so the folder of table A is where all the files are located. So all these files are inside this table. And then also in the metastore would track partitions. Okay, so and in each partition would generally be files put in a particular also subfolder. Okay, so then essentially inside the table A folder, you might have a folder for different partitions. So we'll say like, state equals Ohio. So that'd be one folder for all the people in Ohio, and then another folder for all the people in Connecticut, and another folder for all the people in Florida. And essentially, this is essentially how your files would be organized. Okay, so essentially on your data lake, you'd have a folder for the table, and then each partition, each sort of subsection of that data set would be in a subfolder. And that worked. You'd be able to kind of query the data but the Hive Metastore only kept track of folders. So if I wanted to update the one particular record, so one voter I wanted to update that's in this particular file, I can't just update this one file. I'd have to basically rewrite this partition. Okay, so I would basically make a copy of this partition, make my edits to that file, and then we'd have to swap them out. Okay, so I'm essentially rewriting the whole partition to edit one record. Okay, so that necessarily isn't the best, wasn't necessarily super performant when you're trying to make basic small changes. Okay, there were other aspects about how you would have to write your queries to take advantage of these partitions, depending on how you were partitioning. That would make it a little bit more cumbersome to partition. You had consistency issues, because if I wanted to update data in two partitions, so if I wanted to update data in Ohio and Connecticut, I would have to do one and then do the other. It wouldn't necessarily do both partitions in one transaction. Okay, I could do an atomic transaction for Ohio data, because it would, create a copy, then swap it out. But then I would have to do that separately for Connecticut. So then there's that time difference in between. So basically there's an inconsistency between the moment that the Ohio partition's updated and the Connecticut partition's updated. Okay, so the hope was for there to be sort of a better way of doing this. Okay, instead of tracking this by folders and having to do all these like folder level operations, which also allowed the way query engines would query it, they'd have to actually like say, hey, here's a folder, let me list all these files. Okay, let me list all the folders that are in that folder. There would always be these file operations that also were pretty processing intensive and made things take longer. So there's just like a lot of things that didn't really make this practical. So in this data lake world, data lake houses weren't the thing yet, because this just wasn't a way to get the kind of performance and flexibility you need to really take those data warehouse workloads and make them possible, from your data lake repository. So then, like, over there at Netflix, they're trying to tackle this problem, and they kind of come up with this architecture. Okay, so how about we say we don't care where the files are specifically located? Okay, so we're not going to care about the specific folder setup. I mean, they could be organized into partition-based folders, but it's not necessary. Instead, what we're going to do is we're going to create a metadata layer. Okay, so essentially, first we'll show you sort of the high level. Essentially, we're going to have a metadata layer that allows a query engine to know about how these files are partitioned, where these files are located, what ranges of data these files hold. So that way, instead of actually having to go like parse through all these files and figure out their folder structure to figure out, hey, which files I want to scan, a query engine will just take a look at the metadata. The metadata is going to have all this sort of like summary type information. So think about like an index at the back of a book. You're not going to read through the whole book to find a particular thing. Instead, what you do is you go to the back and you have this nice index that summarizes where you can find what, so you can quickly find it. This metadata kind of operates as sort of a large-scale index in many ways. So now the tools can go in there, scan the metadata, and then it'll know exactly which files to operate. Now, how does it do that? Let's break it down specifically how Iceberg does that. Okay. So generally what happens is that you have your query tool, which could be like something like a Dremio. Okay, if you haven't tried Dremio, head over to dremio.com and try out, hit the little test drive button to give it a free try. It's pretty cool. Okay, and I don't say that just because I work at Dremio. I've played with Dremio. I've used it. I do earnestly believe it is a super cool tool that offers you a lot of value and a lot of ways to kind of save money and make your data workflows a lot easier. Like, truly, that's why I'm saying go try it. Okay, the proof is in the pudding. Just try it and you'll like it. But whatever tool you're using, okay, it doesn't matter. You're using Spark, you're using Flink, you're using whatever. What's going to happen is that that particular tool needs to know which, what is the world of tables you have. Okay, so essentially we're going to have sort of one sort of place where we track what tables exist in your data lakehouse world. Okay, and this is referred to as the catalog. Okay, and this is going to be typically some sort of mechanism that's just tracking. Okay, so one mechanism that exists out there is called Nessie. It's built for being a Iceberg catalog. Okay, but it could be other things like AWS Glue, DynamoDB. There's a REST catalog. There's a variety of different options on what you can use for this catalog. But we're going to say Nessie for this one. This is the one that I'm most intimately knowledgeable about. Okay, so basically what's going to happen is that this Nessie catalog tracks what tables there are. Okay, So then what would happen is that your query engine would go say, hey, I'm looking for table A. Okay, where's table A? Okay, and what Nessie or the catalog contains is essentially the names of the different tables, okay, and then a location of where the metadata for that table is, specifically a file called a metadata.json. Okay, so in this case we have a file called metadata.json. And essentially think of this as like a top level file, okay? It not just describes sort of, it's going to basically, from this file, I can learn, okay, what is the current schema of the table? How is the table partitioned? So what is the current like sort of partitioning rules? Is it partitioned by state? Is it partitioned by zip code? Is it partitioned by date? How is this table partitioned? And it's going to have a list of snapshots. Okay, that's another cool thing about doing it this way is we can track what the table looked like at different points in time. So every time the table changes, we create what's called a snapshot. So think of a photograph of that point in time that we can then say, hey, let's go take a look at the table back like a month ago or 2 days ago. Okay, because we have a list of those historical views. So essentially, the engine is going to go to the catalog, say, hey, where's table A? Well, the table A metadata is here. Okay, and then once it reads that, it's going to look for whichever snapshot it wants to look up. So is it going to look up the most current picture of the or state of the table or any previous state of the table? So then what's going to happen is we're going to have what's called a manifest list. Okay, and that is essentially a single snapshot. Okay, so each manifest list file is going to represent a single snapshot. Okay, and basically it's going to have data about how different groups of files. So essentially what happens is that every group of files that are part in here are tracked in another set of files called manifest. So I really kind of need to introduce both for this to all sort of make sense. So a manifest is a list of a group of data files. Okay, so basically, let's say, you know, these 4 files are in one manifest, these 4 files are in another manifest, these 4 files in another manifest. So this manifest list would list those 3 manifests saying, hey, the table currently is made up of these data files that are listed in these 3 manifests. And generally the manifests are written sort of in a partitioned way. So essentially like probably all the Ohio, if we were partitioning by state, was going to say, okay, well, this manifest list covers everything with these partition values. So we'll say Ohio. Okay. And then have another one, I'll say like, okay, well, this manifest covers data for Connecticut. And this manifest covers data for Florida. Okay. So basically, let's say my query is, I just want to get the voters in Florida. Okay. I just want the voters in Florida. It's going to know, oh, I only need that one manifest. The other 2 manifests that cover Connecticut and Ohio, I don't need. So we'll skip those. So all the data files associated with those manifests, I don't need. So then it's going to go here. Okay, and be like, okay, I only need voters in Florida, which is under this manifest. So it's only going to look at that manifest, which has a list of each individual file with additional data on what data is inside those data files. So I still haven't actually touched the data files yet. So now we're taking a look at the 4 files that represent data in Florida. Okay. Then what can happen is that maybe my query says, I want all voters from Florida who live in Orlando. Okay. Or let's say the zip code for Orlando. Okay, so now what it can do is it can go, there'll be metadata on the zip code field saying, okay, each data file, each of these 4 data files covers zip codes between this range to this range. So maybe only one of those files actually has zip codes that cover that specific Orlando zip code that I mentioned. So in that case, it's only going to scan that one file. So basically using this metadata, the query engine is able to sit there and say, I really only need to scan this one file when everything comes down to it, because these files don't cover the, Ohio which cover Ohio and Connecticut are not in the partitions that I'm particularly scanning. So we're able to do partition pruning at the manifest list level. And then once we start looking at the individual manifests, we can determine, well, these 3 files don't have values, even though they cover Florida, they don't have zip codes that are relative to my query. So really only this file is important. So now the query engine can only run the query on that one Parquet file or ORC file, and that's a much faster operation. So by having this layer of metadata that allows the query engine to sort of more smarter plan the query, you're good. You're going to get a much better performance for your query. Okay. And that's pretty cool. Okay, so that's like the point. Okay, so it's this metadata layer. So at the end of the day, like your actual data, you're not writing your data to Iceberg files. Iceberg is not a file type. You're still using Parquet. So the same Parquet files you've been using or the same ORC files you're using can be used with Iceberg. It's just whether you're adding this metadata layer that allows engines to read that data faster. Okay, because it can think through it more intelligently. So let's clear this out for a moment. Okay, and let's just see what happens if, walk through what happens if we were to create a table. Okay, so again, we have our catalog. So let's say I did want to create like a table. Okay, what does the engine do if it's working through Iceberg? Okay, well, here's the thing. First, I'm going to create the table. So that first table operation, there's no files created because the table is supposedly empty in that first operation. Okay, so essentially what's going to happen is we're going to create our first metadata.json for table A. Okay, so we'll say metadata.json v1. Okay, and then we're going to update the catalog and say, hey, catalog, this is currently the metadata file. Okay, and there's nothing else that needs to be created because there's no data files because we haven't added any data yet. And if there's no data files, there's no manifests because we're not tracking any data files. And if there's no manifests, there's no need for a manifest list. Okay, so right now that's it. So now let's say later on we're going to add data. So let's say we add all that data that we mentioned before. Okay, so then what would happen is at first, before it does anything else, it's actually going to write up all the data files. So first thing it's going to do is write all those Parquet files. Okay, so we'll say, hey, we're going to write all these files. Okay, we'll just make 8 files for now. And then what it's going to do is that it's going to start grouping those files depending on how the table is partitioned into different manifests. Okay, so let's say this is one manifest. Okay, so that's going to be one manifest. Now let's just put this. And then here we have another manifest. Okay, so we have these 2 manifest files that track these particular groups of files. Okay, then we would create a snapshot that keeps track of those 2 files. So we would create a manifest list. Okay, so we'd create the manifest list, and that's going to track these 2 files. And then we need to create an updated metadata.json. Because the previous again, you never change files. Okay, you're always necessarily, the way this works is everything's immutable, meaning not changeable. So anytime you need to change something, you recreate it. So in this case, since the previous metadata.json.v1 wasn't aware of this manifest list because it didn't exist yet, we create a new metadata.json we'll call metadata v2. And then what we do is we tell the catalog going forward that table A is really using this metadata. Okay, so we just move the pointer. The catalog is now pointing to that version of the metadata. So now the next time that someone wants to query the table, the catalog is going to point them to this metadata.json, not this one. And that's how the engines always know what's the most updated version of the data. Okay, because the catalog is always going to make sure that you're referring to the newest metadata.json. So now let's say we add another 4 files. Okay, so we do another transaction. We add some data. Okay, what's going to happen is we'll add that data, and then a new manifest list is created. Okay, and this new manifest list is going to track all the previous manifests. So these previous manifests will still be there because that's still valid data. Okay, and we'll also track the new manifest with the new data files. And again, then we create a new metadata.json, metadata.json.v3. Okay, and then that would become the new pointer. So now the table point, the catalog is going to point there. So the catalog mechanism is basically the source of truth. Like, hey, what is the correct metadata to look at? The catalog is the arbiter of that. That's why it plays such an important role, because it enables the consistency between all your tools. Because I could have done this transaction in Spark, but then if I go do a read immediately with Dremio, it's going to basically query the right files because the catalog is the undisputable arbiter of what is the latest metadata. So essentially, this is like the architecture of like how Apache Iceberg works. There's a lot more to it. If you want to learn more about like how you would optimize these tables, how these files work, what's inside these files, go check out Apache Iceberg, the definitive guide. You can scan it right there. There's the QR code. Also, make sure to follow me on LinkedIn if you don't already. I'm always constantly posting content around the data lakehouse, whether it's on Apache Iceberg, on Nessie, on Dremio, on all sorts of great data lakehouse stuff. And make sure to also subscribe to a couple podcasts on iTunes and Spotify, including Gnarly Data Waves, Data Nation, and Select Star from Data.Lake. Subscribe to those 3 podcasts on iTunes or Spotify to hear a lot more great content. And thank you guys for listening. If you guys enjoyed the video, leave a like, leave a comment, share the video, and thank you very much.